And in the case of continuous distribution, we know that the number of x values, the number of possible x values is infinite. Even if you give me a small line segment like this, there are infinite number of x values within the two bounds. And we call this a finite continuous distribution. Again, you can see that the upper limit is way below infinity. Yeah. So even if you put 5 million, 5 gazillion on the right point, maximum right point here, doesn't matter. It's still below infinity. Whereas in this case, sort of like a bell curve, it actually goes to from minus infinity to positive infinity. So in this case, it's an infinite continuous distribution. So infinite or finite is actually talking about the x-axis again. So we actually don't quite talk much about the y-axis in terms of discrete, continuous, finite, infinite. We do talk about the y-axis, however, and that will be where we spend a lot of time on. Now, the y-axis, for discrete distribution, the y-axis is the probability. This, I hope you get it on day one. Okay, so this is the probability. For discrete case, probability. Yeah. So for discrete case, the height of the graph is the probability. When we talk about the function fx, y equals to function fx, it's kind of like, well, am I drawing just a general graph, right? No, but if we talk about the height of the graph, height of the bars, then that refers to the probability. Okay, actually the bars is also quite misleading. It's very common to see that in textbooks, in slides, in lecture slides, and here in my slides too, because it's also a common way to present it, to make sure that the heights are quite visible. However, seriously speaking, to correctly draw this probability distribution, it should be just a series of points, because the bars carry no meaning at all. We don't need the bars to support that height in that sense. So it's just a point floating up there, but it looks strange. And if you present it to an audience from far, it may not be very visible. So we often draw a bar to show and make it visible, but you should understand that only the height that makes sense is the information that is conveyed. The bar itself, and more importantly, the misleading part is often how fat or how skinny the bars are, as if the width of the bars conveys some sort of a meaning when actually it has no meaning whatsoever. All right, because the value x takes up a point value. It is not a range value. And even if we say small values of dice, we have already grouped the 1, 2, and 3 into one point called small. So no matter how you call it, whether it is a number 1 or a qualitative label like small or a label like red, R-E-D, it is a point value. So in that sense, the width of the bar has completely no meaning, and therefore sometimes it's misleading, because for visual um, attractiveness, we kind of like to fatten it until they are joined together. Yeah, because when you draw skinny bars, it's just very fragile. But no, all right, you need to tell yourself when you are the consumer of such a graph that it's only the top point that counts, the height that matters. Clear? All right. Sometimes the bars are drawn in such a way as if they occupy a width of 1, and thereby giving the sense that the area is the probability. Actually, no. Yeah, again, no. Discrete diagrams, discrete distributions, discrete histograms, height represents probability. Now, why am I spending so much time trying to emphasize that when, if it is the case, when it's the same for continuous distribution? And actually, no. For continuous distribution, the height is not the probability. It is called the probability density function of x. So in short, it represents the probability density. It is as if it's like If it's very high, then it's made of lead. It's very dense. 1 gram of it will weigh a lot. Yeah, it's like a density. And if it is very low, then it's made of cotton. All right, so this part is made of cotton. Let's look at this. So this part is like, it's cotton, it's very light, and this part is made of lead. It's super dense and so super heavy in terms of the weight. So you can think of the height as the weight per unit, per unit what? Per unit width, and the width is so small that you can just cut a thin laser slice of it. Yeah, so it's non-zero width, but almost zero visibility. So the height represents probability density, how heavy it is, how tall it is. So PDF equals to height, yes, and that much is correct. Therefore, when we want to draw and show a bell curve, we have to calculate the height, right? So that we have the x and the height and the y, and then we can plot that point. To calculate the height, we calculate using the PDF, the probability density function of the continuous distribution. PDF is not defined for discrete distribution. Instead, if you like, we just call it the P of x, the probability of x taking up the little x value. Some textbooks will call this the probability mass function, as if we continue using the physics definition of density, and now we kind of give it some width, some volume, so that it actually weighs with a probability. That's why it's called probability mass function. But if you don't like that, just stick with probability. All right. So because that is what we're after. If the probability is high, it's very likely to occur, then we decide to do or not to do, and so on. So let's come back to continuous distribution. If the height doesn't represent the probability with which we use to make important decisions, then what represents probability? It is, that's right, some of you were already talking about it, the area. Yeah, the area. So the area will represent the probability. A bigger area, a more likely scenario. A smaller thin area, a less likely scenario. So far, okay? Now, let's take a look at this uniform distribution, this block diagram here. The wider it is, obviously, the more likely the event. Yeah, so basically, it's quite visible, except it will be two-dimensional. And the width matters now. Whereas in the discrete case, the width of the bar doesn't matter. In the continuous case, both the width and the height matter. So in the case of bell curve, we can ask, what's the chance that large values occur? Right, so we are asking about this area here. Find the area of this part of the diagram. That's it. So we're converting an abstract notion called probability into a geometrical notion called the area on the diagram for continuous distribution. Okay, and therefore, as you can see, for continuous distribution, we have to find area and we cannot add up the heights. Yeah, so we basically just have to find the area of the given curve. Finding area, we can use the simple geometrical concept, like for instance, find the area of this red block. That's easy, right? Length times height. And length times height comes from integration because we have done it already, so we know it is length times height. What about this part of the diagram? Well, it's complicated, right? So we will have to use integration. And for simple curves, we can do integration. Maybe your university professor has given you some simple height functions to integrate. Yeah. For complicated height functions, we will use software packages like MATLAB, Python, R, or other packages to do numerical integration so that we can get the results quickly without having to bother with the integrals and various mathematical formalities, and we can quickly get the answer, the area, with high accuracy and speed. Yeah.